Thanks a lot for the introduction. So let me just, because of the audience, just briefly begin by talking really quickly about another theory of replication in Newtonian theory. And everybody who has studied the stability of the solar system within Newtonian theory would know that small devices are inevitably their presence. And in fact, they can be seen as your enemies in trying to prove the stability of the solar system in Newtonian theory. I will hopefully argue now that in relativity, small devices are maybe eventually your friends for that particular problem I'm going to introduce. Okay, let's now jump directly into relativity, general relativity. So by definition, this is the theory formulated by Einstein in 1915, and by definition, it's the study of the equation which Einstein wrote down back then, more or less. And in vacuum, it takes the following form, namely that the Ricci curvature tensor equals a constant lambda times the metric. So lambda is called the cosmological constant, and for the purpose of the talk, we can rescale units such this can take either the value -1, 1, or +1. And the unknowns of the equations are a smooth four-dimensional manifold M equipped with a Lorentzian metric G. So the metric G is Lorentzian. This means that the signature of that metric is -+++. So that is, of course, rather different from the maybe more familiar Riemannian metric, where the signature would be ++++. So in that metric, this equation becomes actually a nonlinear, quasi-linear hyperbolic PDE. Unlike, let's say, in the case where this is a Riemannian metric. So the natural question one has to address when one has a PDE, what is the natural well-posedness theorem for that equation? So let's remind ourselves again, what is a natural well-posedness theorem for a linear hyperbolic PDE? So maybe from your undergraduate course on PDEs, you would know that this equation actually box phi equals 0, which I now wrote for a general Lorentzian metric, but actually you can think of this as just being a more complicated form of the standard wave equation you might experience. In particular, if G is the trivial Minkowski space-time, then in fact this is the associated operator. And this is called the Laplace-Beltrami operator, you maybe know from Riemannian geometry, and for that signature it becomes a hyperbolic equation. So this equation is well-posed when you additionally to phi, you also have to place initial data on a so-called time slice or an instance of time. For that equation, it means that we specify a spatial slice, and we have to specify phi and the derivative of phi. Then this equation is well-posed. So for the Einstein equation, the following theorem gives well-posedness, and this goes back to Choquet-Rohat. This is it was given in 50-60s. It's quite a long time, from 1915 until 56, before well-posedness of that equation has been established by mathematicians. So so what is the well-posedness statement? Well, we take suitable data. Well, what should the data be? Well, we just want, in some sense, a geometric version of that. So what we want is a three-dimensional time slice. So this would be a three-dimensional Riemannian metric. Moreover, we also want the derivative of phi. So kind of for this equation, we want the derivative of G. So this is just the second fundamental form. So this will be initial data. So a three-dimensional Riemannian metric with a two tensor. So for suitable such data, there exists a unique maximal space-time M for G, solving star this equation. Okay, and then of course we want that actually this is the initial data, so that this embeds into M4. So that theorem gives you now the well-posedness theorem of general relativity. So now this also solves the question of local existence and local uniqueness. So one immediately can ask the question of what is the global behavior of solutions of this? So what about global existence and global uniqueness? So regarding global existence, of course, everybody who has studied in quasi-linear hyperbolic PDEs would know that in generally global existence is false. And indeed, also there exist explicit solutions of this, and black hole solutions, for which global existence is false, and the spacetimes are geodesically incomplete. But nevertheless, one can study the stability of such explicit solution, of such explicit black hole solutions. So in my talk, however, I'm not going to talk about the global existence problem, but rather the global uniqueness problem. So let me give you a kind of hopeful conjecture, which you would like to be true in order to address the question of global uniqueness. So like this. So for all data, kind of the unique solution predicted by that theorem, MG4, is inextendable. Say now is C0. Oh, okay. This one is inextendable with C0 metric. So if true, this theorem would tell you the following: that for all such data, in fact, this maximal solution predicted by the theorem is in fact truly maximal in the sense that if it is incomplete, which might happen, then indeed it is incomplete for good reason, namely that the spacetime is in fact C0 inextendable beyond the incompleteness. And that kind of physically speaking or formally speaking would correspond to a scenario where an observer, because of the incompleteness, might reach the boundary of that future spacetime, of that spacetime, that such an observer will be truly torn apart by infinite tidal deformations. So this kind of would really give a strong version of predictability of the classical theory of gravitation. And so it turns actually out, so if true, this would be nice, if you like predictability of the equation. It turns out, however, that this for all, it turns out that fact that this conjecture is how I stated is unfortunately not correct. Indeed, the most important solution of the answered equation, namely the Kerr black hole solution, which is an explicit solutions of this equation, in fact is C infinity extendable. And by the Kerr solution, I mean truly that you take complete initial data, so everything you can possibly give for that explicit solution, and you get an explicit four-dimensional spacetime, which I call Kerr, and that four-dimensional spacetime is C infinity extendable, and moreover, each such extension is highly non-unique. So this, in that sense, the above conjecture is manifestly false. Let me also mention that, sorry, but I have to mention it, so that we call, if the cosmological constant is negative or positive, then we don't call it Kerr, but rather Kerr ds or Kerr ADS. Nevertheless, okay, this is just if you have seen this. So here, I mean truly that all of those Kerr solutions which corresponds to either of those cases have this property that they're C infinity extendable, and that's a problem if you like global uniqueness. So in fact, this conjecture can be already saved if you like that. Okay, let's forget about Kerr, and let's say at least maybe generically this holds true. And there's also good reason why this conjecture should be true. Can you explain again what you mean by extendability, or what? By extendability? Extending what? So you get a space-time here. So this is a manifold M equipped with the Lorentz symmetry. So the manifold itself, the smooth structure, that is trivially extendable. That's never the question. The question is whether the metric G is extendable. So I mean the obvious. What? So the manifold is embedded in something? Well, this would, I mean, it's the obvious. I mean, the question is whether there exists the map M G into another one, and G, where such that this embedding is forward. I mean, it's the obvious version of an extendable. Where the other map is, where the image of the map is not the whole thing. Okay.
And you'll clarify what you mean by generic, I'm sure.
Well, I mean, that conjectural statement has actually, yeah. I mean, now I've clarified this, and generically, this would have to be addressed if you were to prove such a conjecture. But how I stated the conjecture, actually, if you want to prove that, then you truly have to specify what you mean by generic. However, it turns out that the conjecture I stated is now, It's also false. This is a theorem by Luke. Indeed, if you were to prove this conjecture in the affirmative, you would answer this in the affirmative, then you would have to prove that it's generic. Then you would specify what you mean by generic. Of course. Before I would have to say that this actually is a so-called strong cosmic censorship conjecture, and this goes back to Penrose. Here, this regularity class, one can debate what you actually meant initially. Maybe it's not the C01, but C01 is the one you would like to be true. But actually, it turns out, as I already mentioned, that that conjecture is false. So I say the C0 formulation is false for lambda equal to 0 and 1. And in fact, they prove that this behavior you experience at Kerr, that you see infinitely extendable in non-unique manner, that actually is robust to perturbation in the sense that perturbations of Kerr initial data lead to a solution, which is again C0 extendable across that boundary. And that's why this conjecture is false. And they actually also give a proper open set of initial data of around Kerr, such that occurred at ES, such that this conjecture is true. In that sense, you don't, if you falsify the conjecture, you don't have to specify what generic is.
Well, but in which topology is that, Phil?
I mean, this is a higher order Sobolev norm.
Okay, so the open set is actually some smooth category.
Yeah, I mean, these kind of these estimates you prove they're always in some sense with Sobolev norm. So it's so yeah. I mean, okay. So the question is, what happens for lambda equal -1? So this theorem falsifies the statement for lambda +1 and 0. So the question is, what happens for lambda equals -1? And I see. Okay. So and this is actually what I've wanted to talk about. And in fact, the dynamics of this equation, if you're in that space, if you have this cosmological constant, they're more unstable, much more unstable. So, because I don't have so much time, let me give you a theorem. Namely, the linear strong cosmic censorship conjecture is true. So by this I mean, that we take not this equation, but actually this equation first. And this is always the first step in order to study this fully nonlinear equation. One really has to understand well what is the behavior of solutions to this equation on that specific background. And before we have not understood this sufficiently well, there's no chance you can close the above theorem, because you would always kind of well, not always, but essentially most of the stability proofs are really propagating this behavior for that equation. Okay, so the linear strong cosmic censorship is true, meaning that that fields blow up in amplitude. So this would correspond to that C is not C0 extendable. And this, of course, corresponds to the fact that the metric is not C0 extendable at the boundary of space-time. So what's the field? So that's a solution to this equation. But maybe I didn't specify it properly. Of Kerr ADS, parameter polarized by angular momentum A and mass M. If M and A are in set P, where P satisfies the following property, is very generic. P is a subset of R2. It's not whole of R2, but rather it is actually, in some sense, all possible parameters. One can study this.
Is it related to the angular momentum?
Yeah, A is the angular momentum of the black hole, M is the mass.
Psi something like a conformal factor?
Psi is Psi. Yeah. So Psi is just the solution of generic solution of this equation.
Yeah, but what's the connection to the metric?
The connection is, if you look at the principal symbol of this equation, and this is actually this. So this equation, if you write it in harmonic coordinates, the principal symbol will be a Laplace-Beltrami operator acting on the metric coefficients. So what you really have to understand first is, what is this behavior?
Okay, but there's no geometric connection to the.
I mean, there's the connection that if you want to study this, sorry,
you're just analyzing it.
Exactly, I'm just analyzing it. And the question, I mean, it's the scalar analog of this conjecture. Right. I mean, it is truly the scalar analog. And actually, this theorem was preceded by the the theorem on that level for this equation, and also the tools have been used here. Anyway, so it's the back exceptional. So now, kind of everybody who, I have a negative time, right? I think. Okay, just maybe 2 words. Don't have to write anything. So now everybody has studied kind of small devices problem would know that those notions of genericities, those competing notions of genericity appear very naturally in small devices problem and associated Diophantine condition. And in fact, something like this also happens here. And the reason is that there are 2 sources of instability, namely some quasi-mode instability on the exterior of the black hole and some scattering poles on the interior of the black hole. And whether those sources of instability are sufficiently strong now kind of will boil down to a non-Diophantine condition on the black hole parameters. And whether this condition is fulfilled or not, gives rise to a set P which has these properties. So in that sense, kind of to roll up with this, with what I started, the strong cosmic censorship you like to be true, because that will give you a strong version of determinism. That holds true if the small devices problem is present. And in that sense, I would like to say that in this case, they are your friends, the small devices. And yeah, let me conclude my talk here. Thanks.
I'm a bit confused, if I can ask a question, Peter.
Please.
Please, Peter.
Yeah, in the classical case,
So what do you mean by class?
these are competing. So, like in KM theory, the small divisor problem, which is Lebesgue typical, is very different to the small divisor, which is Baire typical. Because the one is like a Liouville number, and one is like a hard to approximate in a Diophantine sense. So what's happening here? Are they both favorable?
So here what's happening is you like to prove an instability. That's your goal, because you want to prove that the quantity blows up in C. And it turns out that, I mean, and that's very different from, let's say, KM theory, where you actually like to prove stability.
Right.
So that's why I'm saying that the small devices are your friend in this case, because what you want is that you want to prove that C goes to infinity, and that is connected to two sets, and they one discrete set in the exterior, which are scattering poles, and one quasi-discrete set on the exterior, which are quasimodes. And whether those sets accumulate sufficiently fast at infinity, because they're infinite, they're discrete sets on the real line. If they do, then indeed the resonance, they create a resonance which is sufficiently strong as to show that this blows up. And currently this is still work in progress. I claim that if you take the complement of that set, so that will be a set which is Baire meager and Lebesgue has Lebesgue full measure, then in fact you get that C remains strong in the interior.
Okay, so if I understand, then you do extend this result to lambda. The instability is essentially at the linear level extended. Is that correct for these?
So I didn't hear what you said about lambda, because sorry.
You're dealing with lambda equals -1.
Right. Yes, lambda -1 is important. Yeah.
And are you actually showing at the linear level, which is what you're describing here, I guess?
Yeah.
That it is unstable.
Right. That's what I'm saying. Yeah.
Yeah.
I mean, actually, to address this problem in the full nonlinear, is very interesting, and much easier problems are still very open.
Yeah.
Because the dynamics of this space of the spaces are much more turbulent, or whatever you want to call it.
Okay, thanks. Thanks. Very, very interesting.
Thank you. So thank you very much. Oh, was there a question? Sure.
So I guess just two questions. So when you say linear, I guess you're doing everything perturbatively.
I mean, I just look at this equation on the fixed background. If you want, you can think of this as perturbation. Yes.
Okay, so that's the analogy with K, and I guess.
Yeah.
And then just does this include also the case of non-rotating black holes?
No, for non-rotating black holes, you actually don't have this problem. I mean, it's first of all, the non-rotating case is a non-generic case because this is really A equals 0. And for this, actually, you don't have this problem of C infinity extendability. You have a strong singularity. I mean, actually, oh, let's put it this way. For this, this conjecture is trivially true.
Okay.
For the Schwarzschild background.
You say you are using harmonic coordinate. Does this case the code can cause a problem near the boundary?
So I'm just giving you, yeah, I mean, if you want to, I mean, this is not what I use here, but in harmonic coordinate, you can see that this equation is true. When now, if you really want to prove theorems about low regularity statements of this, then indeed you have to be very careful what coordinates you choose and whether those coordinates are okay, because you have to be able to write down this equation, and yeah, that's a problem. Yes.
So what does maximal mean in the?
Yeah, that's a great question. And so this is a question going back to Leray on general hyperbolic PDEs. So this means global hyperbolicity in particular. So you want that the uniqueness you get of that spacetime. So sorry, so the spacetime you get will be necessarily global hyperbolic. That's what you mean by maximal. And then of course maximal means the thing that you cannot embed into a bigger manifold. But you want in particular that this is globally hyperbolic, and that is also why you get something unique.
So, very stupid question, but what's the difference between maximal and an extended?
So you will, I mean, so here you get a maximal spacetime. So that spacetime is maximal and okay, and it has certain properties. But the question is whether that max spacetime is inextendable. And in fact, it can be the case, and this is the case for this scenario, that the spacetime you get from data, which are Kerr, you get the Kerr solution. That Kerr solution is maximal because it's the maximal development of those initial data. However, it turns out that that maximal development is smoothly extendable in a non-unique fashion, and that is the issue of. Sorry.
Okay, so I guess we stop now because we have to hit cookies at 3:50. Yeah. Okay, so.